Okay, now I want to talk about the notion of a minimal spanning tree and an algorithm called Kruskal's algorithm to find it. So first, let's just look at a spanning tree, and I'll consider a tree that's built on the complete graph of some points in the plane here. And what I mean by the complete graph is just that I'll consider a graph of all the edges that are possible between all the nodes. So there's n choose 2 or O of n squared possible edges between all these nodes. So I can connect any two nodes I want. And so let me just try to create a spanning tree that way. Okay. So I guess first I'll choose, to connect 2 and 5. So in my union find data structure, which I plot up here, I see that 5 and 2 are connected. 5 now points to 2 as a root. 2 still points to itself as a root. Okay. Next I'll add 8 and 3. So now 8 points to 3 as a root. Now add 3 and 1. So now I see that 1 points to 3 as a root. 8 also points to 3 as a root. 3 points to 3. Okay. 0 and 6. 1 and 7. Now this is interesting. I actually added 7 and 1, but because of path compression, I ended up, I'm doing my fast union find here with path compression. Actually ended up connecting 7 to 3, which is interesting. So 7 directly has 3 as a root now. Okay. I do that. What did that do there? Oh yeah, that connected that little component of 0 and 6 to this component. So now these are all connected. Okay, but I can't do this because I'm going to create a cycle. So if I added 6 to 7, I would create a cycle. I would be able to go from 6, 7, 1, 3, back to 6 again. So I'm not going to add that. That was just some other edge I tried to throw down, but I couldn't. But I can throw down that edge. I can throw down that edge. I can throw down that edge. And guess what? I'm done now. Okay, so I haven't created any cycles, and after this step, everything is fully connected. So that's a spanning tree. But I don't really love this spanning tree. It's a little messy. The way it's been drawn here, it has some crossings. Some of the edges overlap each other. It almost looks like 3 is connected to 7, but it's not directly. It's actually the edge from 3 to 8 there. So that's a little weird. Also, it seems like I chose long edges. So if I had to pay a cost for each of these edges that was proportional to the distance of them, it seems like I'd be able to do better. In fact, it seems like I could just maybe, I don't know, what's a silly little thing I could do here? Well, this edge is definitely longer than the edge from 5 to 6, so I could get rid of that. This edge is definitely longer than the edge from 6 to 7. So I could also, instead of connecting 6 to 3, I could connect 6 to 7, and that connects this component here. And then if I did that, I could connect 0 to 7. That's shorter than 0 to 6. Okay, so there seems like a lot of things I could do to make this better. And so what I'm sort of getting at is the notion of a minimal spanning tree, which means out of all the edges I have available to put down in my graph when choosing a subgraph, let me try to find those that create a spanning tree which minimizes the sum of the lengths of the edges. And so actually the algorithm to do this is incredibly simple. It's called Kruskal's algorithm. And instead of just throwing down like the edges in some random order and checking the cycle condition and the connectedness condition as you go along, this time we're actually going to throw down the edges in increasing order of length. So we're going to sort the edges by length first, and we're going to start by adding the smallest edge. So if I look at this, it looks like the smallest edge is going to be between 0 and 7. Oh, okay. Or 8 and 9. That was pretty close. I bet you the next one's going to be 0 and 7. Yeah, there we go. All right, so now I keep adding the edges in that order. Now, it's really the same algorithm that you've already implemented. I just checked to make sure I'm not going to create a cycle as I go through. So I don't add an edge if it'll create a cycle, but if it doesn't create a cycle, that's great. I'm getting closer. And you see the edges get uniformly longer and longer. So there were some cycles I was going to create. There's a nice big old cycle I would have created. So don't add those, but then I add that. Don't add that. Don't add that. Boom, I'm done. Okay, so this one is a little bit better than the other one. In particular, what I see is that the distance is only 2.24, whereas the distance in this one ended up being 4. And the other nice property that it has is that it doesn't have any crossings. So that's cool. That's a little bit more difficult to prove, but I'll hint at it a little bit later in class. Okay, so and that's really, it doesn't have any crossings for this graph that I draw in the plane. Although again, remember these nodes and edges can be anything. They could be people in a social network, and the edges could be friends connecting to two people who are friends, and the weight of the edge could be like, I don't know, if we're thinking of minimizing things, maybe they have a smaller weight if they're closer to each other, more closely connected, or a larger weight if they're further apart, like they're not really super good friends, they're just kind of distant. So we might be trying to figure out, well, which friends should we have talk to each other if we're doing Whisper Down the Lane? Well, I guess not a linked list, but just if we're trying to connect everyone by connecting people in pairs who are most similar to each other. Okay. But here, I just think it's a little easier to visualize when we talk about adding edges in a complete graph of points in the plane. But just bear in mind that graphs are much more general than that. Okay, so that's Kruskal's algorithm. It's a greedy algorithm that adds edges in increasing order of length. But otherwise, it's exactly the same. As we're adding edges, we make sure that we're not going to create a cycle. So we don't add an edge if it's going to create a cycle. And then we just keep doing that until the whole thing is connected. So let me look at another example here. Let me run Kruskal's algorithm. Let me maybe just a bigger graph just so we can see what that looks like. So I'll do it on 30 nodes now. Okay, so we start off with a lot more nodes. Oh, this is this is not the good one. This is like adding them in some random order. And actually, yeah, you can see that this actually, it's hard to see, but this is a spanning tree. There are no cycles here, and eventually, well, yeah, it's not yet, but eventually it'll be fully connected. This is pretty horrible. So let's see, that ended up being 16.4. Actually, I want to save that. This is a good example. It gets to be even nastier as you add more edges if you do it randomly. So yeah, so here's just some arbitrary spanning tree. Looks terrible, but it actually does satisfy the properties of connectedness and no cycles. So I could hang this up and it'd be a tree, okay, from one of these nodes. But let me sort the edges first and do this again. So now I add the edges in increasing order of length. So if I do that, so there's the first one. Okay, that's pretty small. So I'm going to start by adding these really small edges. And I kind of start off in these little clicks here, but yeah, okay, I could still make a cycle. I'm storing a lot of information here about, the union find data structure, just keeping track of things that are connected so I know if something's going to make a cycle or not. So you see, yeah, I avoid adding edges if they're going to make a cycle. A bunch of cycles in a row there. But I'm slowly starting to connect things. And eventually, I'm going to connect. It's going to take a little while. But eventually I connect the whole thing. So that was the last holdover there, was that too. Okay, so look how nice this is compared to the other one. So the other one ended up taking, oops, let me get there. So that ended up costing 16.4, and it looked like a god-awful mess. This one, look how much smaller the sum of the edge lengths is. 3.97 versus 16.4. And just look how much nicer, because again, it has no crossings. And it's laid out very nicely. You can just see that you didn't take any edges that you need to. So that's Kruskal's algorithm. And you'll be using Kruskal's algorithm in assignment 5 for a slightly different purpose, not for building a spanning tree, And it's a slight variation on it because you're actually going to be creating new nodes. So you're not just creating a spanning tree of a graph, you're actually using Kruskal's algorithm on the back end to connect things, but you're actually building a tree based on that. But you definitely have to understand Kruskal's algorithm first, so I wanted to make this module to help you. Okay, but actually I don't feel the need to give a module exercise on this because you're going to get plenty of practice with it. I think if you're able to implement union find in the last exercise, you'll be fine. So, but I do want to talk about a little bit of theory, so I want you to continue on to the next video following up on theory. Okay.